This segment we're going to talk about the simple Rankine cycle or the steam cycle, and we're going to kind of walk through step by step the four processes of a simple Rankine cycle. We're going to look at it on a TS diagram. We're going to look at where this is used in the real world, and then we're also going to talk about just small tweaks that we can make to that simple Rankine cycle to increase the thermal efficiency. All right, so the simple Rankine cycle, let's look at it and follow along on a TS diagram. The first process from state 1 to 2 is an isentropic compression within a pump, and of course that requires some amount of work into it. Unless it's otherwise noted, you can go ahead and assume that the quality at the inlet of the pump is 0. So you've got a saturated liquid going in. With a pump, you don't want any bubbles, right? You don't want any gas bubbles to form. So it's either going to be from a saturated liquid to a compressed liquid or a compressed liquid to a compressed liquid. Then you've got a constant pressure heat addition in a boiler. And that heat addition may come from a nuclear source or a geothermal source or fossil burning fuel or something like that. And this all takes place at constant pressure. And we're going to end right here on the saturated vapor line. We don't necessarily have to. We'll talk about that in just a second. So that's my state 3. And then I've got this high temperature, high pressure steam, and I expand it through a turbine, get some work out of it, end up at state 4, and that's an ideally isentropic process, so it goes straight down on the TS diagram. And then I go through a condenser, which is just a heat exchanger, which condenses the steam all the way back to a saturated liquid, and that takes place at constant pressure. Now, the way that the condenser works is it's sort of, you've got two streams that are transferring heat between each other. So you've got the steam in the Rankine cycle, or the water in the Rankine cycle, that loop 1, 2, 3, 4. But then you might have this other separate loop of cooling water, and those two streams don't necessarily come in direct contact with one another. They don't come in direct contact with one another. So we'll work a problem like that involves calculating things with that cooling water. And if you need a review on how heat exchangers work, there's a review video in the Thermal 1 review video section. All right, so where might you see this in practice? This is a Rankine cycle that's used in conjunction with a nuclear reaction. So this is sort of like what you would see at McGuire, a really simplified version of what you might see at McGuire Nuclear Station, which is right down the road off of Lake Norman. On the left-hand side, you've got the nuclear part of things. So you've got a nuclear fission reaction, generates a whole lot of heat, and your Rankine cycle, which is in the middle, and we'll walk through that in just a second, is the power cycle. It harnesses the heat, converts some of it to usable work, and then rejects it to a low temperature reservoir. The low temperature reservoir being the water that's sort of that it's not really a loop, but sort of the almost closed loop on the right hand side, the warm water. So that's running to the cooling tower. So let's kind of walk through this cycle. Number 1, you've got an isentropic compression through a pump. You've got a constant pressure heat addition within a boiler, and it's picking up heat from that nuclear reaction, although the water that's in the Rankine cycle is not in direct contact with whatever, with the water on the primary side, the water that's in contact with the control rods over there. And then those are expanded over the turbine, which ideally would happen isentropically, and then it goes through a condenser. They've just drawn it as a box here, and that occurs at a constant pressure. So that's where you would see it. That's one place that you might see it in practice. All right, so let's look at the equations that we can use to analyze these guys. So you've got an isentropic compression in the pump from state 1 to state 2, and that pump operates, if I draw my control volume around the water that's flowing through that pump, I've got an open system. I'm going to assume everything operates at steady state. It's isentropic, so I can go ahead and get rid of those Q's. It's a work in, not a work out. And I'm going to go ahead and ignore kinetic and potential energy changes. So all I've got left are the m dots and the h's. And if I apply my conservation of mass, noting that everything occurs at steady state, I can replace those m.1 and m.2s with just an m dot. Since that pump operates isentropically, ideally, it would have an isentropic efficiency of 1, which of course we'll analyze pumps that do not have an isentropic efficiency of 1. But if it does operate isentropically, so isentropically means that everything's happening reversibly, and we are analyzing this cycle as if it takes place at steady state. So steady flow, reversible work. This is equal to the isentropic work of the pump, and we have an equation for steady flow reversible work. And there's a review video if you need in the Thermo 1 videos regarding steady flow reversible work. In that particular video, you see a negative in front of that integral VdP. It goes away because we're using subscript convention. So that W would become work out minus work in. So the negative would go away. All right, now for a pump, because the thing that you're compressing is in a liquid form, this is an incompressible substance, so the specific volume doesn't change that much. So you can also express the work in terms of in terms of the specific volume and the pressure change. So this is little w at the very bottom, and then we've also got things written in power up top, the W dot N. That would be in kilojoules per second, and the equation on the very bottom, that would be in, say, kilojoules per kilogram. All right, oops, let's go in the right direction. Then you've got a constant pressure heat addition within the boiler. So if I apply my first law, and I get rid of the DEDT term, because I'm assuming everything operates isentropic, or not isentropically, but at steady state. There's no, there's a Q in, there's not a Q out, there's no work, and I'm ignoring kinetic and potential energy changes. Then I'm left with this guy right here, and if I apply my conservation of mass, I can get rid of the m dot 2 and m dot 3 and just replace it with m dot. All right, 3 to 4 is an isentropic expansion within my turbine. Oh, and before I go too far, keep in mind that up until this point, we've been analyzing gas power cycles where your working fluid is air and it behaved as an ideal gas. That is not the case anymore. So when you look at, say, the isentropic compression in a pump or the isentropic expansion in a turbine, the entropy, if it's isentropic, the entropy is not going to change from the inlet to the outlet. So, for example, with this guy right here, the isentropic expansion within a turbine, if you apply your first law, this is the guy that you get. And between state 3 and state 4, the entropy doesn't change. So S3 and S4 are equal to one another. If you have an isentropic efficiency, then you would need to use that isentropic efficiency to calculate state 4 for the actual process. In that case, the entropy would not be the same. All right, and then the last process, you have a constant pressure heat rejection process in a condenser. So from 4 to 1, the pressure doesn't change. And if I apply my first law, I would get, if I apply my first law and the conservation of mass, this is the guy that I would get. Variations to increase the simple Rankine cycle, variations on the simple Rankine cycle to increase the thermal efficiency. So I've got a picture of the Rankine cycle, or the simple Rankine cycle, up at the top, and the TS diagram, at least the TS diagram for the cycle that we looked at, where we were just, when it went through the boiler from 2 to 3, it stopped right there on that saturated vapor line. But we could superheat the steam, and in that case we call that heat exchanger a steam generator as opposed to a boiler. I'm not really going to nitpick in class, so if you call it vice versa, if you call both of them steam generator, that's fine too. But this superheats the steam and it increases the net work output. So you got 1 to 2 and then 2 to 3, except instead of stopping on that saturated vapor line, it keeps on going into the superheated region, and it superheats the steam. And then the rest of the cycle sort of, falls into place where you would think. And it increases that work output because the enclosed area on the TS diagram is equal to the Q net M, because remember, this is a reversible process, or a reversible cycle. And if you remember the equation for, look back at your video from Thermo 1 on the equation for calculating entropy change, you could get that in terms of TDS and Q. So that kind of goes back to that. So if you need a refresher, that's you can go back and review review the video on the definition for an entropy change for a reversible process. But anyway, so the enclosed area here, this is the Q net in, which for any cycle is equal to the work net out. So if I'm increasing the area within the confines of that area, then I'm increasing the work net out. I could also increase the steam generator or the boiler pressure, and that just means I'm pushing that line of constant pressure up, and so I'm increasing that enclosed area as well. And then I could do the same thing at the bottom. I could decrease the pressure in the condenser, and that would push that line of constant pressure down, and that would also increase the enclosed area, thereby increasing the network output. All right, well, the next time that we see each other, we will work some problems like this, and in the next video we'll talk about how we can modify this simple Rankine cycle and add things to it in order to increase the thermal efficiency. Thank you very much for watching.